Okay, now this is the one that we are going to start. You see the problem I put it on the Moodle website for the tutorial section, and I changed the rate of energy. The first one is 0.15 rand, 0.1 meaning 15 cents per unit, while the second one is with rand 1.5 meaning 1.5 rands per unit. The result is different. So that's the demonstration. We will practice this one. The second one, you will start the second one. So this minute, I'll come after that. What is given there, just read it. The cost of line conductor is given, and 200,000 A plus 1,000 per kilometer, and A is in square centimeter. That we always need to take note of what is the unit of A. A is in square centimeter. The interest and depreciation is given 10%. It's a 3-phase 33 kV system. The maximum kVA for the year is given 7500 maximum kVA, and what else is given? Form factor 1.13 for a load factor of 60%, and loss factor is given 0.2 KL, which is the load factor KL, and 0.2 KL plus 0.8 KL squared, and cost of energy is around 1.5 per unit. Resistivity of conductor material is 1.76 times 10 to the power minus 6. We have to find out the most economical cross-sectional area of the conductor. Is that okay? If you have anything that you did not pick up here, please let me know. We can go to the first step. So the first step is to calculate the current. It's going to be IM, because it's the maximum kVA. We get current from the kVA, because it is maximum kVA, we get maximum current. So it's 7500. If you remember the formula that came from yesterday, divided by √3 times the voltage, which is 33 kV, and it will be within bracket. So 7500 divided by √3 divided by 33 kV. Calculate this and tell me the value quickly. (131.21 ampere). That's correct. Right, now we come to the next step, which is to calculate the IRMS. IRMS is going to be equal to KL, which means the load factor, times form factor, form factor, times IM. So what will be its value? Load factor is 60%, so it's 0.6 times form factor is given 1.13, and the current that we got 131.2 ampere. So it will be 131.21, and that gives what value? What is the value of IRMS? Calculate and let me know. (88.96) is the value of the current IRMS. When you got the IRMS, we can go to calculate loss factor, which is lambda. I'm just writing in words because writing words here is very challenging, so I'm writing it in number. So what is given there? 0.2 KL plus 0.8 KL squared. So what it will be? 0.2 times KL is what? Load factor, which is 0.6 plus 0.8 times KL squared. KL is 0.6 squared. What is value? What should be the final value of loss factor lambda? Point 408. Okay, then the answer will be different. I think I made a mistake in my calculation. The 229.6, 229.586, that's not going to be the correct answer. I'll have to change it. We'll change it when we go to that stage. So this loss factor, please write it down what I'm writing here. This loss factor lambda will be multiplied with the time of R, time in hours, meaning 8760 later on. So this will be multiplied with the time in hours of a year, right? So the next step will be to calculate the resistance of each conductor. The same thing that we consider for each and every problem. So it's rho L by A. So rho is given 1.76 times 10 to the power minus 6 over L. Let me put the L. L is not known, so we can assume it 1 kilometer, because if we go there, the cost of line conductor is in kilometers. So if we choose 1 kilometer, it will be easy for us. So over A is many ohm. But now for 1 kilometer, and the resistivity is in centimeters. So 1 kilometer. Now this needs to, oh sorry, I have to write down again. Let me write it down again. That kilometer needs to be converted to centimeter. This is the problem with the resistance of each conductor. R is 1.76 times 10, 10 to the power minus 6 times 10 to the power 5, because it's 1 kilometer divided by A, the cross-sectional area in centimeters. We assume the length of the line is 1 kilometer. You could choose L kilometer as well, like we did in other case. They will cancel each other on either side. So it will be equal to, the R value will be now equal to what? 0.176 over A ohm. Do you get this value? Does everyone have this value? Okay, so we have the resistance of each conductor. Let's go to the next step, which is the calculation of cost of interest and depreciation. Cost of interest and depreciation is how much? It's rent. We can take the part directly which has A in the expression, meaning 200,000 A, and the interest rate is 10%. So multiplied by 10 over 100, and for each kilometer is that rate. So we have 1 kilometer. So we can say we multiply it by 1. This will remind us it is for how many kilometers, what is the length of the line. If we miss this one, we might be correct in answer, but next time if the length of the line is different, we will forget for other examples. So that's why I keep that one as 1 kilometer. So what will be the answer for this value, this equation? Tell me the value of this expression, cost of interest and depreciation. $20,000 A. So 20,000 A. Did I write it correctly? 20,000 A. Yes. So that's the cost of interest and depreciation. So when we're done with that, we can go for cost of energy wasted. We can go for cost of, let me clear all these things, it won't be enough space. Cost of energy wasted, like R annum. So what it will be, three-phase line, so 3 I squared 8.96 squared. So that's 3I squared. Now we have R. R is 0.176 over A. That is R. That okay? Then time is 8760 hours, but we said that there is loss factor. Loss factor was 0.408. Remember that lambda will come here, 0.408. So that's that, and then you multiply it. I just unclicked it, so now it's not allowing me to type there anymore. It has to be now multiplied by 10 to the power minus 3. So let me type it once again. 3 times 8.96 squared times 0.176 over A, which is R, times 8760 times 0.408, which is T, and then you multiply it by 10 to the power minus 3 for kilowatt hour part, and then you multiply it by the rate, which is 1.5 rand per unit. So what is the value of this one? You calculate and tell me. When you have the value, let me know. 22401.6 or 0.59. Now that it's now using, next step is to write it. It is now using KEL, meaning Kelvin's economy law, that 20,000 A is equal to just 20,000 A. If you remember, 20,000 A is equal to 22401.59 over A, and from there we can calculate A. So what's the value of A? 1.06. Everyone got that value? 1.06. What's the unit? Centimeter squared. 1.06 centimeters squared. Right, so if we used, instead of 1.5 rand per unit, if you used 0.15 per unit, what would be the change here? This whole equation will change to 0.15. Do this calculation just now. If we change this one to 0.15, what will be the value of A? We change this value to 0.15 instead of 1.5 rand. If we use 0.15, what will be the value of A? Calculate and let me know. .33. Is that everyone getting the same answer? Is everyone getting the same answer, 0.33? Okay, that's good. So I'm just keeping this on for 1 minute more, maybe, for the ones who are a little bit slow can write down, and then I'll go to the next slide. How to get lambda again? Lambda is given there, loss factor. Can you see the equation? 0.2 KL. You see the lambda equation, let me clean it up. You see the lambda equation is given there, loss factor lambda. So what is happening here? Loss factor lambda is given there in the problem. What it says? It says is equal to 0.2 times KL. KL is the load factor, which is this load factor KL. KL is the load factor, is stated there. KL is equal to the fractional load factor, meaning 0.6, because it is 60%. So that's the first part, 0.2 KL plus 0.8 KL squared. So times 0.6 squared is that clear? That should give you that value of 0.408, and this lambda will in turn be used to multiply it with the number of hours in a year, which is 8760 hours, will be multiplied by this 0.408, which is the lambda. Loss factor is related to the number of hours. The higher the loss factor, the number of or the amount of energy wasted will be larger. Right, so we can go to the next one. Is that okay? Okay, let's go to the next one. Okay, let me update this file. So I corrected the values there for the answer. Check if it is appearing here. Yeah, 1.06 and 0.33 change because I change some numbers all the time. I changed some parameters in the tutorial all the time, so that's why the answer is different. Now it's updated. We can go to this next one. It's something similar, it's a little bit different. So this one is saying what? It's giving same thing. Cost of line conductor 200,000 A plus 1,000 per kilometer, interest and depreciation 10%. A is also in square centimeter. We must always take note of this. I always repeat when I'm going through all this tutorial that we must take note of where A is related and what is the unit of it. Three-phase 33 kV line, maximum kVA is also given 7,500. It's the same tutorial. Form factor is given 1.13 like the previous one. Load factor is 60% like the previous one, but no loss factor mentioned there. Can you see the difference? No loss factor mentioned here. Meaning there will be that 408, that loss factor that you just asked will not be part of this problem. So you calculate everything from the very beginning. Like we have it already, so we can use those previous data. We have IM, maximum current. What was the value? 131.21 ampere. Write it down as I write. It's the same. You have the formula from the previous one. Everything is same. Only the loss factor is not mentioned in this tutorial. Only the loss factor is not mentioned. Can you pick up that? So we have the IM from the previous calculation, previous tutorial, because everything I kept same because we don't want to spend time unnecessarily. If we can use the same data from the previous one and make something different to understand the difference between them, what happens. So when we have IM, we can calculate the IRMS. What was the value of IRMS? 88.96 ampere, if we remember that value. It 8.96 ampere is RMS value. Right. So from there, we can go to the next step. The resistance of each conductor. Which is R is equal to, we still remember that value 176 over a ohm. We have it from there as well. Can you find that out from your previous tutorial? We assume the length of the line is 1 kilometer. We're doing the same here. We're keeping the length of the line to be same. So we have resistance, and then we can find out the cost of interest and depreciation. is how much? Is equal to rand 200,000, sorry, 20,000 A. That's what we calculated, taking only the part which has A. It was 20,000 A from the previous one, if you remember. The interest rate is still 10%, is the same, no difference here. And then we can go to the next step. Okay, let me keep it as it is. And then I can use another block here to say cost of energy wasted. The line per annum is equal to 3 times I squared, meaning that it's 196 squared times R, which is 0.176 over A, times time, which is 8760. In this case, there will be no loss factor involved, so it's directly only 8760 hours. Then after that, we have it for that kilowatt hour part, 10 to the power minus 3. Then we have the rate of energy, which is 0.15. In this case, it's 0.15. So what is the answer? You will find out. I'll have to correct the answer again. It's written 165 there. I'll have to correct this one. So cost of energy wasted is how much in this case? Tell me the value. $5.9058. Is that correct? 5490.58 over A. That many rand. Sometimes to write here rand. Now we can equate it with that equation that was 20. What is happening here? Why it doesn't have 20,000 A is equal to 5490.58 over A. Is that right? Sorry, 5490.58 over A, and from there we can calculate what is the value of A. Point 0.524. So it's 0.524. Is everyone getting that one? What's the unit? Centimeter squared. You must not forget the unit, because if you say 0.52 what centimeter squared, meter squared, or millimeter squared, you need to make it right all the time. So I'm keeping it for a minute for everyone to write it down. After that, we will go to the next one. What is saying what happens to the 1000, the cost of line conductor? That's the constant part. That 1000 is there, that's the constant part. That constant part is not related to Kelvin's economy law. Kelvin's economy law is dealing with the cross-sectional area of conductor, which is the most economic part. So the cost that we incur in the process of buying a conductor, installing it, or laying a cable, including the cost of tower, and it is independent of the cross-sectional area. That 1000 is independent of cross-sectional area. A is not there, so we should not worry about that. We can ignore that one. That's why we don't need to consider when we writing it in this equation. It's this part that is A, meaning it's going to change or it's going to determine what will be the economic cross-sectional area. But there is no A here, so what is the point of considering that or worrying about that? Is independent of A. Does not matter what the cross-sectional area is going to be, the economic one, it's not going to change this 1000 or 10,000 or 100,000, whatever number is there is not going to change, or that number is not going to change or determine the value of A. So that's why you don't need to worry about that. Okay, so let me do that part again. So it's 0.5 to 4 now, it's fine. We can go to the next one. You see what is happening here. The cost per kilometer length of a three-phase overhead line is 250,000 A plus 12,000, where A is the cross-sectional area of each conductor in square centimeter. So the cross-sectional area of the conductor is given in square centimeter. The load factor is given as 50% for the load current. So load factor is given 50% for the load current, and that for the losses, meaning the loss factor is given as 0.2 plus 0.8 F squared. Is something similar to the previous one, where F is the fractional load factor. In that case it was KL. In this case they wrote it capital F. In the previous case it was KL load factor. In this case it's capital F. Combined interest and depreciation is given as 9% per annum. Cost of energy is 12 cents per unit. Resistivity of the conductor material is also given, which is 1.76 times 10 to the power minus 6 ohm centimeter. We always need to make sure that we consider the units all the time. So we have to find out the most economic current density, meaning I over A. So what is the first step? Again, we can choose the length of the line. It's not given. We select 1 kilometer. We make it easy for calculation. So we can do the interest and depreciation. So annual charge. I'm writing different words for different problems. They are same. We say cost of interest and depreciation. Sometimes we say annual charge for interest and depreciation. They are same, because if you go from place to place, they will use different words. Annual charge of interest and depreciation is how much? It will be rand 250,000 A, 250,000 A times 9% in the interest rate, so it's 9 by 100, and it's for 1 kilometer, so that one is going to be there all the time. so that we don't forget that there is that length involved in that calculation. So what is the value of 1? What is the stage? Two 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 five 22, so it's rand 22500A. So the cost of interest and depreciation done one part. So we can go to the next step to find out the loss factor, load, call it loss factor or load factor of losses or loss factor. Sometimes we call it load factor of losses as well. It's the lambda, the same thing. So what's the value? 0.2 times load factor is 0.5, 50%. So that's that multiplied 0.2 times 0.5 plus 0.8 times f squared. F is 0.5 squared. You get it now? The same that we used in the previous one. Right, so what's this value? 0.3. That's the correct answer. Everyone should get this value. .3. So we can go to the next step, which is resistance of each conductor. Is R is equal to rho L over A. Rho is given 1.76 times 10 to the power minus 6 rho times L is 1 kilometer. 1 kilometer is how many centimeter? 10 to the power 5. And over A, rho L over A, we convert it to centimeter because it's in kilometer there, and it's given in ohm centimeter, so we have to convert that into centimeter, so that the units are cancelled and we finally get ohm. If you forget how you remember, you see what is there, ohm centimeter, right? 1.76 into 10 to the power minus 6 ohm centimeter. So centimeter is there at the top numerator in the first place, and A is in square centimeter. So what is happening? A centimeter is remaining at the denominator, and then you put this one in centimeter, they will cancel each other, and then you get the ohm finally. That okay? So what's the value of this one? It should be again 0.176 over A. Is that right? We got the resistance, and when we get the resistance, we can go to calculate the cost of, let me go there and decide, cost of annual cost of energy wasted in the line. So it will be equal to 3 squared R. I is what? We don't know. So I remains I. Where on the side you will write that the RMS value of current is I ampere. RMS value of current is I ampere. I squared. R is 0.176 over A. I squared R. Now we're coming to the time. Which is 8760 hours in the first place, and 8760, the loss factor will come here. What's the loss factor? Which is 0.3 times 0.3. Then you multiply by 10 to the power minus 3 for kilowatt conversion. 10 to the power minus 3. Right, and then you multiply it by the rate of energy, which is 0.12. So what's the value of this? What's the answer for this step? 0.16. Everyone is getting the same. 0.167 I squared over A. That's what she's saying. Can you check it for correctness? Everyone must get the same answer. 0.167 I squared over A. That's what she's saying. I need to see at least one or two people answering the same. Can you hear me? I'm very soft in my voice as compared to the voice that I use in classes, because I'm sitting in a room. Otherwise, I'll feel that I'm shouting. Okay, well, if we get that one, now our next step is to use KEL. So we'll say here, now using KEL, what we do, 0.167 I squared over A is equal to that cost of interest and depreciation that we got, 22500 A. And when we have that, we can calculate I over A. So you tell me the answer of this one, I over A, because we're calculating the most, this is the most economic current density. What's the answer? I over A is most economic current density. $367.05. Is everyone getting that? $367.05, and the unit is ampere per centimeter squared. The unit will be what? Is ampere per, let me write it here. These things is very challenging. Ampere per centimeter squared, because the current and the cross-sectional area is in square centimeters. The ampere is the current, which is ampere per unit area, and the area we are dealing here is in centimeter squared. So ampere per centimeter squared will be the unit. Right? Did everyone get it? That's good. It's 2 o'clock today. I have 2 more tutorial that are not related to this Kelvin's economy law. I'm keeping this one for 2 more minutes. If someone is a bit late, they can write it down. They are not related to Kelvin's economy law, but they are 100% related to the fundamentals of power systems, and we need them everyday operation of our power systems life. And those are in this tutorial. You can calculate at home if you get time during the weekend. One is to calculate the megawatt and megawatt consumed by an RL load connected to a 3-phase voltage of 345 kV with resistance of 202.98 ohm and inductance of 0.1815 Henry, and the frequency is given as 60 Hz. So you have to calculate the megawatt and megavar that will be consumed in this 3-phase 345 kilovolt system when the resistance and inductances are like that. And the next one is there on the Modulo website. Next one is the opposite. The megawatt and megavar are given, and the phase voltage is given, frequency is given. You will have to calculate the R and L opposite, meaning we need to know when there are some R and L, how much is the active power consumption, how much is the reactive power consumption. It's the opposite. If we know that the active power consumption is this much, reactive power consumption is this much, then what is the value of resistance and inductance in the circuit? So you try at home. I did not give answer in this one, in these two you can see. So you try it at home, and then we'll discuss them on Monday in the morning. Once we are done with these two, these are not related. I will not ask you in test or exam or whatever. I always do that, but we need to learn these things. So we make sure that these are so fundamental. So we'll finalize these things on Monday, and then once we are done, then we'll go to the next chapter, sag and tension material. But on that day, before sag and tension chapter starts, I'll give you another presentation which will be covering the aspects that comes from practical industry. So thank you very much. If you have any question, you can ask before I close. So it's fine now. Thank you.